All right, so we're going to talk about understanding limits graphically and numerically. And we did some limits in pre-cal, so this should be a nice review, and then probably take it a little bit farther than we did in pre-cal. Okay, limits are the backbone of understanding that connect algebra and geometry to the mathematics of calculus. In basic terms, a limit is just a statement that tells you what height a function intends to reach as you get close to a specific x value. And again, that height function or that height value is going to be your y value. Recall from pre-cal that you evaluated 3 types of limits, and we're going to complete this table. So a right-hand limit, the proper notation is the limit as x approaches some number, we're going to just let it be c, from the right, so we put that little plus sign, of the function f of x. Verbally, it is the limit as x approaches c from the right of f of x. The left-hand limit is the limit as x approaches c, and then you do the little negative sign of f of x. And this is going to be the exact same thing we're just talking about from the left. Then the general limit when you're looking at the limit from both sides. And for that limit to exist, it has to approach the same place. So this is the limit of f of x as x approaches c. So we're going to begin our discussion of limits by analyzing a rational function because they have a lot going on. So we're going to take this rational function. I've already got the graph over here, but we're going to kind of fill in this table, and this is all information that we covered in pre-cal, so this should be a wonderful review. So we're going to talk about asymptotes and holes and domain and range. So remember, to determine if something is a hole or an asymptote, you need to factor it and see if any pieces cancel. So if I were to factor the top, so it gives me 9 and 1, I want a negative 9 and a positive 1, and the bottom is just squares. So then I know that those two cancel. So I know that I have a hole at 3 comma something, because the x equals 3, which comes from the x minus 3, is the part that canceled. What's left is what we're going to use to figure our vertical asymptotes. So for the vertical asymptote, you take the bottom and set it equal to 0 and solve it. Okay, but remember, we're not going to use this piece because it canceled. It's a hole, not an asymptote. So the vertical asymptote is going to be x equals negative 3, which came from him. Horizontal asymptote, that's where you look at your powers, and you can see that the power on the top of the original and the power on the bottom of the original are the same. So this is that y equals a over b. So y equals 3, because it'd be 3 over 1. So now we're going to work on finding the y value of the whole. So I'm going to take what was left after I factored and canceled, and I'm going to plug the 3 in to see what his y value is. So 3 times 3 is 9, plus 1 is 10, and 3 plus 3 is 6. So that's going to reduce to 5/3. And you can see, so that would be 3 and then 1 2/3. And that's right about here where this hole is. Okay, So now for my domain and range. So for my, hold on. I need to make this darker so I can see it. These are, that's your x-axis. Oh, no. The asymptotes and the axes are running together. There we go. Okay, so those are my asymptotes. Okay, so yes, now that point makes sense. 3 and then 1 and 2/3 right there at the hole. Okay, sorry. All right, so for the domain are all the x values. So all of these, let's see, let's do it this way. All of these x values are going to be used except -3. So my domain is going to go from -infinity to -3. I'm going to hop over -3 because it's an asymptote. And then it's going to pick back up and go to the hole. So I'm going to go to +3 because that's the x value of the hole. And then it's going to pick back up at 3 and head on to infinity. The range is going to be, let's see, all of this all the way to that y value. And then I'm going to go to the asymptote. And then I'm going to go the rest of the way up. So the range is going to be from -infinity, and again I hit the hole first, and that y value is the 5/3. And then I pick up with the 5/3 and head towards the asymptote at 3, and then pick back up over the asymptote, after the asymptote, and head to infinity. Okay. So now let's take this function. Now that we've figured out all his information and we could have graphed him, even though that was provided for us, now let's use this function because it has some interesting things going on, and let's talk about limits. So let's revisit the notation we learned in pre-cal. We need to convert these old methods of explaining extreme behaviors into limit notation for use in calculus. So use the graph to complete the table below. So it says, as x approaches -infinity, the graph of f of x approaches. Okay, so as x approaches -infinity, what is the y value that the function is approaching? And it is approaching this asymptote, which is a 3. So the answer here is a 3. But we're going to turn around and write it using a limit. So I'm going to say the limit of f of x as x approaches -infinity is 3. So now as x approaches infinity, so now we're headed this way. And I want to know what the function is approaching, and it's approaching that horizontal asymptote, that's the y value. So that limit is also a 3. So I'm going to say the limit of f of x as x approaches infinity is 3. Okay, so now we're headed to -3 from the right, and I want to know where the graph is approaching. So let me erase some of this. Okay, so as we approach -3, so there's the x value that's -3 from the right. So I'm coming in from this side. So here's my graph from the right as we approach -3. This graph y value is headed to a -infinity because it's headed south. So I can write the limit of f of x as x approaches -3 from the right is a -infinity. All right, as x approaches 3 from the left. All right, hold on. As x approaches +3 from the left. Okay. +3, that's this guy right here, from the left. Okay, so from the left. Now, it won't ever get to 3, but as it approaches 3 from the left, we are approaching the y value of that whole, so that's 5/3. So this is the limit. X approaches 3 from the left of f of x equals 5/3. Okay, now we're headed to -3 from the left. So -3 from the left. So there he goes. He's headed to positive infinity. So I'm going to write the limit as x approaches -3 from the left of f of x equals positive infinity. All right, now we're headed to +3 from the right. So +3 from the right, we are also headed to that y value of that whole. So this would be the limit as x approaches 3 from the right of f of x equals 5/3. Okay. Can you explain what the value of a limit represents in terms of the graph? Okay, so the value of the limit, first of all, is a y value. The limit is a y value. And it's not the y value of the function at that particular x value. Just because, remember, this was a whole. So it technically doesn't have a y value there. So it just wants to know what you're approaching. So the limit is the y value that the graph is approaching from both sides, if it's a general limit, from both sides of the, and I'm going to call this the target value, and that's just x equals c. So it could be an asymptote, it could be a whole, it could be a defined value. If you read down here at the bottom, it says informally a limit is a y value which the function approaches as x approaches some value. The limit as x approaches c if f of x equals L means as x approaches c, f of x, which is y, approaches the y value of L. Okay, so this is just being able to talk the talk and walk the walk with limits. Okay, so now we have this really fun function. It does all kinds of stuff. And we're going to find not just all kinds of limits, but if you look at A and B, those are actually just function values. So it's to make sure that you understand the difference between f of 2 and the limit as x approaches 2. Okay, so say you want to find the limit as x approaches 4 of f of x from the right. The positive sign in the limit notation indicates a right-hand limit. We already know that. If you think of a function as a highway and imagine you are traveling along f of x towards x equals 4 from the right, not to the right. So the plus sign is from the right. Okay, so let's try some of these. So if I want to find f of 2, this is not a limit. This is just wanting to know what is the y value when x is 2. Here x is 2, and the y value is going to be right there at -1. B, I want to know f of -1. So here's -1. F of -1 is not going to be that open circle. It's that closed value right there. So his y value is a 4, not a 2. Okay, so C says I want to hit 4 from the left. So the x value, that's 4. From the left, what is the y value? Looks like the y value is a 3. And feel free to pause this and see if you can figure it out and then play the notes and see if you get these right. Feel free to do that for this whole section. Like put it on pause, run through A through N, and then hit play and double check yourself. So for D, I'm headed to 2 from the right. And again, this is not the same thing as F of 2. I just want to know, as I fly in towards 2 from the right, what Y value is it approaching? And it is approaching 1. Okay, let's see, I'm going to erase that. Okay, so now I'm headed to 2 from the left. So 2 from the left is going to be right there at -1. All right, -1 from the right. -1 from the right. And again, I could care less about that dot up there. I want to know if I'm headed towards -1, what is the graph approaching? It's approaching a value of a 2. -1 from the left. Okay, here's -1 from the left, and he is also approaching that 2. All right, -4 from the right. -4 from the right is headed to that Y value, which is a 2. -4 from the left. Well, the function doesn't exist over here. So we're going to put D and E does not exist. Don't put no solution because technically you're not solving anything. We're just simply stating that the limit does not exist. Okay, again, let me clean this up a little bit. -1. Okay, so this one doesn't have a direction on it, so I'm looking at -1 from both sides. So here's -1. So from the right and from the left, it is both approaching a 2. All right, K wants me to head towards a 2 from both sides. So here's the 2. Okay, now this one's complicated. From the right, it looks like it's approaching a Y value of a 1. From the left, the Y value it's approaching is a -1. So the limit overall does not exist. Because for a limit to exist, you have to approach the same number from the right and from the left. So his limit does not exist. Okay, now I'm headed to a 5 from both sides. Now, notice that my graph stops here, but there is an arrow. So that means this continues on. Now at 5, he looks to be down here at -2, and from the right and from the left, that would be the same value. Very different from this end over here that's a dead stop. As x approaches 0, let's see, from the right and from the left, they're both approaching a -1. And as x approaches 1, from the right and from the left, it looks to head towards a -2. I want to compare this one and this one. So I just want to point out the difference between a limit and an F of, a place. This is, where is it? This is, where is it headed? What is it approaching? Which I think we used in our definition of a limit. This is an exact place. Where did it end up? At -1 exactly, where is it? Well, it jumped way up here. But the limit is down here. Where is it approaching? It was approaching here, but when it got here, it jumped up to here. So the limit isn't where did it end up? The limit is where is it approaching? Okay, think about this. If we think of the function as a highway, then the point 2, -1 could be considered the end of the road. That's 2. Okay, this is just a different point. 2, -1 could be considered the end of the road, while the point at -1, 2 is more like a pothole, how could you describe the points located at 2, 1? So our point 2, 1 would be not a pothole, because because it's not a pothole because the road completely breaks. Like, this is a complete break in the road. If it was a straight line that had a circle, like a true hole in the middle of in the middle of a road, like the function keeps going on both sides, that would be this guy right here. Then yeah, this -1, -1, 2 is this guy right here. -1, 2 is a pothole because it's continuous on both sides, and it just has a hole in it, like a pothole in the road. To -1, which is this guy, isn't a pothole. It's just, it's like a dead end. So the point 2, 1, that's this one up here, it's like a dead end because the road does not continue going on the other side. It's a dead end, but it's without a barrier. Because technically this line can get closer and closer and closer to that hole and never get there. The point 4, 3, that's this guy, he's a dead end. Oh, that's not the point 4, 3. Let's see. The point 4, 3 is this guy. The point 4, so that guy isn't a pothole. He's kind of just a sharp turn. No pothole, because there's no hole. If it had done this, then that would be a pothole. And we're going to come up with better words for it than pothole. But I don't think we do that today. All right, so hopefully this analogy gives you a more visual reference for understanding limits from a graphical approach. Let's get a little bit more formal with our definition now. Okay, limits can fail to exist in 3 situations. So case number 1, the limit would not exist if the limit differs from right and left. So if you fly in from the right and you fly in from the left and you're flying into 2 different places, then the overall limit does not exist. So if we look at the limit as x approaches -1 from the right of this guy, of f of x, that's going to give me, let's see, -1 from the right, that's going to give me a 1. Then if I do the limit as x approaches -1 from the left of f of x, that equals a -1. So those are 2 different places. And since these 2 things don't equal, so we would say the limit as x approaches -1 from the right of f of x does not equal the limit as x approaches -1 from the left. Then you would say, therefore, the limit as x approaches -1 of f of x does not exist. And I know that sounds like you're having to put some math terminology on something that's super, super Captain Obvious, but that's how you have to write it when you get to an FRQ in calculus and it wants justification. This last piece right here, that's a whole point. That's your justification. So you have to show what the limit from the right is and what the limit from the left is. You have to state that they're not equal, and then you have to draw your conclusion. So the limit can't differ from the right and the left. Okay, case number 2. And this is a fun word. Oscillating behavior. So oscillating behavior is when it approaches a particular number, and at that number, it looks like it's just spazzing out. It bounces back and forth really, really fast to the point where it's almost chaos. You can't see what it's doing. Oscillating is not like, it's not like a sine curve that just very calmly and chill and bounces back and forth. Oscillating is much more of a spastic behavior. It's this, oh my gosh, in the middle, and you can't see what is actually happening. And of course, this wants the limit as x approaches 0 of f of x, and you would say it does not exist because oscillates. And this is sine of 1 over x, and that's one of AP World's kind of go-to oscillating graphs. Okay, case number 3 is unbounded behavior. And that's just fancy for asymptotes. So the graph is going to shoot off into the land of infinity or negative infinity. Then you can say that the limit does not exist. However, in the future in this course, when it's headed to the same infinity, we are going to say that the limit exists. So this is justify why the limit does not exist at x equals 2. So you could say that the limit as x approaches 2 from the right of f of x is infinity. And then the limit as x approaches 2 from the left of f of x is also infinity. I would conclude, and I have no problem going ahead and establishing this with you guys, that because they're both headed to infinity, I'm going to say that the limit as x approaches 2 in general of f of x is infinity. At the beginning of this course, they kind of have a little asterisk by infinity and say infinity is not a real defined number. Infinity is the behavior. So in my homework, I think you're going to go ahead and see me put infinity for those. But in some textbooks, you'll see here does not exist because in their minds, infinity is not a real place. But you are absolutely fine to go ahead and put infinity. Now, if you had an asymptote and one was headed to positive infinity and the other was headed to negative infinity, then the limits would not be equal because one's headed positive and one's headed negative. So that limit would definitely not exist. So the infinities have to be in the same direction for you to get a conclusion. Okay, estimating limit values from tables. Okay, so now consider the function. This is a rational function. Looks like it probably factors. Complete the table below to find the limit as x approaches 3. So we can type this into our calculator and then go to our table and adjust our table set so we can see these values. I'm going to go ahead and fill these in because I assume that's something that you guys can do and you'll get to practice that on your homework. So again, we're just plugging this into our y equals, we're going to our table, and we're adjusting our table set so that we can see these x values even if it's adjusting them one at a time. So this f of x, this y value is 0.1265. This one's 0.1251. This one's 0.1250. At 3, it's actually undefined. 0.1249, 0.1248, and 0.1234. And just for kicks, I want to go ahead and factor this just so I can have a better understanding of what's going on. 15 would be 5 and 3, and I want a positive 5 and a negative 3. So I can see that at x equals 3, it is a whole not an asymptote. So I know that these numbers, because if it was an asymptote, then these numbers would be getting really, really big. And instead, it looks like it's just jumping over a number because it's a hole, it's a pothole. Okay, so we talk about the limit as x approaches 3 from the left. So from the left would be this way, so we're headed to 0.125. And from the right, we're at 1249, which is the same thing as a 0.125. And again, it's not where it is exactly, but I know that they are headed towards the same place. So even if you wanted to put a 0.1249, because that's what you see with your eyeballs in your table, that's totally fine. But I need your common sense to kick in and say, yes, they're headed to the same place. So I'm going 0.125. So the limit exists, and I just proved with a little pre-cal over there that it is, in fact, a hole. If it's not a hole, if it's going to be an asymptote, and again, doing this over here would tell me that because it wouldn't cancel, then these numbers in my table would be getting like infinitely big or infinitely small, and it would either be headed to infinity or to negative infinity. By evaluating certain types of functions at a particular value, we may not necessarily have sufficient understanding of the function's behavior at a specific point. This is especially true for rational functions that contain discontinuities. Rational functions have the most fun stuff going on, so they are a big topic of conversation when it comes to limits. This is why the idea of a limit is so important. Rather than just going directly to some x value using direct substitution, we can approach a point from either side, get some sense of behavior in the neighborhood, in the vicinity. Look at the photo of the arch support construction for the Hoover Dam Bypass Bridge, 2009. And I know your picture is not super clear, but they're building a bridge, and as of right now, it does not connect. They started from one side and built, and started from the other side and are building, and that's when you really, really hope that your math is right and your engineering is solid, because you need the bridge to meet exactly at the same point. We can tell that where the missing section is going to be. The actual height at that point would be the limit. With limits, we can discuss behavior at a point, whether the point exists or not. With limits, we are looking at the y value the graph approaches, not what the y value actually is at that point. And I feel like we've talked about that quite extensively. When finding limits, ask yourself what is happening to y as x gets close to a certain number. You are finding the y value for which the function is approaching as x approaches some c value. Okay, so here's your limit existence theorem. And this is super important, and we kind of talked about it here. When I said, when they ask you to justify your answer, you have to say that the limit from the right either does or does not equal the limit from the left. And then you can state that the overall limit either does not exist if it's a false statement, or you can say that it does exist if it's a true statement. So that's what this is saying, that the whole limit exists if and only if from the left and from the right are equal. So verbally, the limit as x approaches c on f of x will exist if and only if the limit as x approaches c from the left is equal to the limit as x approaches c from the right. All right. In the box below, complete the sentence in your own words. In order for the general limit to exist, the function... Okay, so here I'm looking for a sentence with very little math symbols. So see if you can write a sentence that tells me why, in order for the general limit to exist, the function must what? So pause the video, kind of write out a rough sketch of a sentence for that. All right, so the function must approach the same y value from the left and the right. Okay, then I'm gonna add this statement. However, the function does not have to be defined at this x value. So that last little part is just extra clarification. But for the general limit to exist, the limit from the right and the limit from the left have to equal. They have to approach the same y value. Okay, so last two. So for number 7, we're going to sketch a graph that satisfies each of the conditions. Okay, so I know you're doing this on your own, but I really, really want you to pause the video and I want you to draw a graph, and it's going to take some erasing and some fixing, and we're all going to have different graphs, but I want you to draw a graph that meets all 3 criteria for each graph. So 2 separate graphs that meet those 3 criteria. Okay, so pause and try. It's going to take a little thinking. Okay, so it says f of a is undefined. So a is my x value, so I'm going to let a be here. So it says f of a is undefined. Okay, so that means x equals a is a point of discontinuity, but the limit exists. Okay, so that's how I know it's a whole and not an asymptote. So I know that the limit exists okay, so the limit from the right and the limit from the left are going to exist. It is a point of discontinuity, and f of a is undefined. Okay, now this says that the limit does not exist. So I can't approach it from each side to the same place. So it has to be a break. X equals a is a jump discontinuity, and f of a is defined. Okay, so here's a, and let's say there's f of a. Okay, so it is defined, but the limit doesn't exist, so that I can't keep going. And it has to be a jump. So let's jump up here. This would have to be an open circle, and then it goes on. So the limit does not exist, true, because from the right and from the left, 2 different values. Jump discontinuity at A, yes, jump from here to here, not removable, it's not a pothole, it's not an asymptote, and f of a is defined. There you go, there it is. Okay, so I hope this was a great review.